Within 4 months, 1 kilometer of Chinese highway had already generated enough electricity to power roughly 800 homes for a year. Now picture what sits directly underneath that same stretch of road. Not just solar cells, but a second hidden layer designed to reach up through solid concrete and touch a car without ever making contact. You heard that right. This is not a theoretical blueprint. Qilu Transportation Development Group built and opened this section outside Jinan in December of 2017, and the figures are certified. Let me tell you what that actually means in plain English. If you have ever watched your range drop on a long drive with no charger for miles, this is the technology aimed directly at that problem. And that is just the beginning. The part almost nobody covers is what this road was actually designed to become. Hit a quick like and subscribe now, because by the end of this video, you will understand exactly how a highway can put power into a moving car. Every EV owner knows the specific dread of watching a battery percentage drop with no charger for another 40 miles. For over a decade, the entire electric vehicle industry treated that dread as a battery problem. Build a bigger pack. Squeeze in more range. Wait for faster charging chemistry to arrive. The International Energy Agency has tracked this approach at a staggering scale. Global fast-charging infrastructure has expanded past several million public chargers worldwide, and the strategy behind almost every one of them is identical. Put the burden on the battery and build enough stations to refill it. Nobody questioned the premise. The road itself was just something a car happened to drive on. It carried weight. It wore down. It got repaved every few years and forgotten in between. Billions of dollars flowed into batteries and charging stations every year, and almost none of it flowed into the pavement connecting them. That premise is exactly what a pavement engineer named Zhang Hongqiao refused to accept. Zhang built his career at Tongji University, studying something most transportation researchers considered a solved problem: how a road surface behaves under stress. Asphalt technology has not changed dramatically in generations, and there was little glory in trying to reinvent it. Most careers in that field are spent optimizing a mixture that has already been optimized for decades, not questioning what the surface is fundamentally for. But Zhang kept circling a question nobody in his field was asking seriously. If a road already survives the sun, the rain, and the crushing weight of a fully loaded truck, why does it do nothing with any of that punishment? Why treat sunlight hitting 5,000 square meters of open pavement as a waste product instead of an opportunity? His answer cost him credibility before it earned him any. Colleagues considered photovoltaic cells structurally incompatible with highway loads. Glass under an 18-wheeler sounded like an obvious way to lose both the glass and the wheel. It was the kind of idea that gets nodded at politely in a meeting and quietly dropped from the next one. Zhang's bet was that the right layering could change that equation entirely, and that a road could become something closer to a power plant than a surface. He was not trying to build a curiosity for a trade show. He was trying to prove that a highway could survive real truck traffic while doing something no highway had ever done: generate its own electricity and eventually deliver that electricity directly into a moving car. That second part, the part about delivering power into a moving car, is where his real ambition lived. Solar panels that generate electricity are impressive on their own, but Zhang's team designed something considerably stranger into the plan from the very beginning: a road that could reach through solid pavement and touch a car without any contact at all. Here is where the story really begins, because before any of that could happen, the pavement itself had to survive contact with the real world first. And that test came almost immediately. France had already tried something like this once, and it had not gone well. A 1-kilometer solar road built into a Normandy highway by the French company. Coils had cracked and degraded under real traffic within a couple of years, and much of the industry treated that outcome as proof of concept, proof that the concept did not work. Transportation engineers pointed to the cracked panels as the final word on the matter, closing the book on photovoltaic pavement before anyone else had a chance to try a different approach. Engineers who followed pavement research will tell you that when Qilu Transportation Development Group announced its own photovoltaic highway in 2017, the reaction from outside China was closer to polite skepticism than excitement. They said the same thing about solar roads that they once said about solar power itself, back when a single watt of photovoltaic capacity cost more than a barrel of oil's worth of energy. We all know how that ended. The Jinan program was not a copy of the French attempt. It was an argument against its central failure. Where Coils had layered thin solar film close to the surface, Zhang's team designed a three-part structure meant to protect the cells rather than expose them, engineered specifically to survive the exact kind of heavy freight traffic that had crushed the French test section. The plan called for 2 full lanes and an emergency lane, 5,875 square meters of embedded panels, built to withstand speeds over 60 miles an hour without drivers noticing a difference from ordinary asphalt. But this was only the beginning of the challenge. Within a week of opening to traffic, one of the solar panels was stolen from the completed test section. A small, almost embarrassing setback for a project meant to showcase Chinese engineering to the world, and the kind of story that skeptics love to point at as proof an idea was never serious in the first place. Here is the detail that puts everything into perspective. Zhang's team did not shut the project down or quietly bury the story. They repaired the section, added protective measures, and kept the road running. The panels that stayed in place kept generating power exactly as designed, straight through winter. What nobody outside the project knew yet was what those panels were sitting on top of. Here is the problem with a road that simply generates power. Electricity flowing into the grid is useful, but it does nothing for the car passing over it unless that car can plug in somewhere. Zhang's team needed the pavement itself to survive a truck's full weight without shattering, while somehow remaining thin enough and clear enough to let sunlight through to the cells underneath. Picture a tempered phone screen. It looks fragile, almost like ordinary glass, yet it is engineered to spread the force of an impact across its whole surface, instead of concentrating it at one point of contact. Drop a normal pane of glass and it shatters at the point of impact. Drop a tempered one and the stress travels outward, distributed across a much larger area, which is exactly why it survives falls that would destroy an ordinary window. That is the same principle behind the top layer of this pavement. A layer of specially formulated transparent concrete sits directly above the photovoltaic cells, engineered to handle roughly 10 times the load tolerance of standard asphalt, while still allowing enough light through to reach the solar layer beneath it. Below the cells sits an insulation layer, sealing out moisture and protecting the electronics from the ground itself. 3 layers, each with a separate job, stacked into something no thicker than a few inches of ordinary road. The consequence of that stack is a road surface that behaves structurally like asphalt while functioning electrically like a solar farm. One driver who tested the completed section described running the car at over 60 miles an hour and noticing the braking distance was almost identical to a normal road. That is not a small detail. That is the entire premise of the project, holding up under exactly the stress it was designed to survive. This was the exact bet Zhang had been defending since before construction ever began. Colleagues had told him the concrete layer alone would kill enough light transmission to make the whole idea pointless. It did not. The completed section generated a peak output of 817 2/10 kilowatts, with an annual output of roughly 1 million kilowatt hours, enough to meet the yearly electricity needs of around 800 households. Solving how a road survives truck traffic while generating electricity is one kind of hard problem. Getting that electricity into a car that never stops moving is an entirely different kind of hard problem, and it is the one most people assume is still science fiction. Here is the brutal catch nobody saw coming when solar roads were first proposed. Generating power at the roadside solves nothing for the car unless there is a way to move that power without a cable, a plug, or any physical contact at all. What if the charging coil lived underneath the road surface itself instead of at the end of a charging cord? That idea sounds like it should not work. Sending meaningful amounts of electrical power through several inches of solid concrete and asphalt into a moving object traveling highway speeds, without any wires touching anything. That is exactly why it does work. The principle is called dynamic wireless power transfer, and it uses magnetic induction. A coil embedded in the road creates a magnetic field, a matching coil under the vehicle picks it up, and electricity crosses the gap without a single physical connection. This is not a concept confined to Chinese test tracks. In France, a project led by Vinci Autoroutes and the wireless charging company Electrion built an active 1.5 kilometer stretch of the A10 highway near Paris, where independent testing from Gustave Eiffel University confirmed sustained power transfer above 200 kilowatts, with peaks exceeding 300, more than double what a loaded heavy truck needs to cover that same distance. That test ran across passenger cars, vans, and heavy trucks alike, all drawing power from the same buried system without a single cable in sight. In the United States, engineers at Purdue University demonstrated a similar system transferring 190 kilowatts to an electric semi-truck traveling 65 miles an hour, roughly the power demand of 100 homes running at once. Zhang's team designed the induction layer into the Jinan pavement from the very beginning, years before most of the industry treated wireless charging as anything more than a laboratory curiosity. That was his second bet, layered on top of the first. Colleagues who had already doubted the solar surface doubted this piece even more. Moving serious power through solid pavement into a vehicle in motion struck most engineers as needlessly complicated compared to just building more charging stations. Zhang's answer was that stations solved the stopping problem. This was built to remove the need to stop at all. A coil buried under 1 test kilometer proves a concept works. Coordinating that concept across an entire working expressway, carrying real traffic every single day in every season and every weather condition, is where most ambitious infrastructure plans quietly die before they ever reach the public. The engineers knew the real challenge was never a single stretch of road. It was building a system large enough for the coil and pavement concept to actually matter. That is exactly what China attempted next, at a scale nobody else has tried. The Hangzhou-Shaoxing-Ningbo Expressway, often called the country's first super expressway, is a roughly 161-kilometer corridor connecting 2 of the most important cities on the Yangtze River Delta, backed by an investment of close to $9.9 billion. Unlike the isolated Jinan test section, this project was designed around a single coordinating question: how do you manage solar generation, energy storage, and future wireless charging lanes across an entire live expressway instead of one closed test track? Here's what most people get wrong about a project this size. It is not just about laying more panels and burying more coils. The old model for EV infrastructure treated every charging station as its own island, a stop you plan your trip around, disconnected from the highway itself, run on its own schedule with no awareness of what the rest of the corridor is doing. The new architecture is built more like a navigation app that reroutes you around a traffic jam before you even see it coming. Except this system reroutes electricity instead of cars, shifting power between solar generation, battery storage, and the road surface based on real-time demand. The road stops being a passive strip of concrete and starts behaving like a single living system, reacting to conditions the way a driver reacts to brake lights ahead. Provincial transport officials have described building a smart, cloud-based control platform to manage exactly that kind of coordination across the corridor: solar output feeding storage, storage feeding charging infrastructure, and traffic data feeding all of it. That kind of coordination did not exist when the Jinan section first opened, because a single isolated kilometer of road never needed it. A corridor spanning 161 kilometers does. If a project on this scale eventually operates the way it is designed to, the generation capacity along just this one corridor would dwarf the output of the original Jinan test section by a wide margin. That is not a modest upgrade. That is an attempt to turn an entire highway corridor into a single coordinated energy system. And the number that came out of evaluating that system needed a second look before anyone was comfortable publishing it. Here is the honest picture. The certified numbers from Jinan are real, verified, and still standing years later. 817 and 2/10 kilowatts of peak output, close to 1 million kilowatt hours generated annually, enough for roughly 800 households, feeding highway lighting, tunnel systems, toll gates, and de-icing equipment directly from the road surface itself. What is not yet true is the headline claim in its fullest form: dynamic wireless charging at highway scale, a car actually drawing meaningful charge while cruising at speed across a real Chinese expressway, remains a stated long-term goal for projects like the Hangzhou-Shaoxing-Ningbo corridor, not a completed operating reality today. The near-term rollout across that corridor centers on solar generation and plug-in charging stations. The induction layer, the part that lets a car charge without stopping, is the piece still being built toward its scale, even though the underlying technology has already been proven at real highway speeds and real power levels in France and in the United States. That gap between what is proven and what is deployed at scale is not a small technicality, and pretending otherwise would undersell exactly how difficult the remaining engineering work still genuinely is. For Zhang Hongqiao, that distinction does not diminish what his team actually accomplished. His entire bet, going back to years of quiet research at Tongji University, was never really about wireless charging on its own. It was about proving a road surface could survive genuine highway punishment while doing something no highway had ever done before. Every number in the story, from the panel that survived a theft attempt to the smart platform being built across an entire corridor, only exists because that first structural bet held. The road did not crack under the truck traffic. If that surprised you, the next part of this story is going to be even harder to believe. Hit subscribe so you are there when we cover exactly how far this technology has come. Bridging solar generation and wireless charging into a single highway is not a story that stays inside China's borders for long. The same challenge at infrastructure. Absorbing the cost currently carried entirely by vehicle batteries sits in front of every country trying to electrify transportation at scale. Every government pursuing EV adoption is essentially solving the same equation. Batteries are expensive, and someone has to carry that cost, whether it is the driver, the manufacturer, or the road itself. Road agencies and energy bodies, from the International Energy Agency to national transport ministries in France, Germany, and the United States, are watching projects like this one for the same reason. Building smarter roads could reduce how much battery capacity every future electric vehicle needs to carry, cutting vehicle costs and material demand across the entire manufacturing sector at once. Here is a historical parallel worth remembering. Rooftop solar panels were once dismissed as too expensive to matter, back when a single watt of capacity cost more than most people would spend on a month of electricity. It took roughly a decade of consistent engineering refinement for that cost curve to collapse enough to make solar power a mainstream part of the global energy mix. The people who dismissed it early were not wrong about the cost. They were wrong about how quickly cost curves can move once an industry commits to solving the problem instead of debating whether it is worth solving. Road integrated energy systems are sitting roughly where rooftop solar sat in its early years, proven in principle, expensive in practice, waiting for the manufacturing and construction costs to catch up to the physics. What makes this genuinely difficult to replicate is not the concept. Any engineering team can sketch a road with solar cells and induction coils in it. What is hard to copy is the structural engineering underneath. The specific layering that lets a transparent, load-bearing surface survive a fully loaded truck at highway speed without cracking. The exact problem that sank France's earlier attempt. That kind of hard-won engineering knowledge does not transfer through a patent filing. It comes from years of failure, testing, and the kind of stubborn persistence that cost Zhang Hongqiao credibility long before it earned him any. The limit standing between where this technology is now and where it eventually needs to be was never political. It was and still is a matter of structural engineering catching up to ambition. And if the idea of a road feeding power directly into a car interests you, the other half of that equation is just as strange. I already covered how China built an electric vehicle where the body itself is the battery, no separate pack bolted underneath the floor at all, and what that means for how power moves once it's actually inside the car is just as surprising as everything you just heard about the road. If you made it this far, you now understand more about road integrated energy infrastructure than most people who write about it for a living. What this technology actually points toward is bigger than any single highway. It suggests a future where the boundary between a road and a power plant stops being a metaphor and becomes an engineering spec, where the infrastructure itself absorbs a burden that has, for the entire history of the automobile, belonged entirely to the vehicle. That shift changes what a road is fundamentally for, and every kilometer built after Jinan today still carries a little of that original bet forward with it. What was actually proven here is narrower than the headlines suggest, and that narrowness is exactly what makes it credible. A road surface can survive real highway traffic while generating certified, verifiable electricity. The wireless charging layer needed to complete the vision has already been proven at real highway speeds elsewhere in the world. What has not yet happened is all of it working together, at scale, on a live Chinese expressway carrying daily traffic. Getting there is mostly a matter of scaling proven pieces, not inventing entirely new ones, which is a genuinely different kind of problem than the one Zhang started with. Zhang Hongqiao built the first piece of that puzzle when almost nobody thought the piece could survive its first year, let alone the years that followed. He is still working toward the rest of it, and what it cost him to get this far was the willingness to be wrong in public, for years, before anyone else agreed he was right. If this changed how you think about what a highway can actually do, hit that like button and subscribe so you never miss what comes next. Now, I want to hear from you in the comments, and I genuinely want both sides represented down there. Should governments prioritize spending public infrastructure money on smarter roads like this one, or is that money better spent making batteries cheaper and charging stations faster? I read every single one. See you in the next one.